Howdy folks, excuse me. We're going to talk today about the titration of bleach. I don't know if it's occurred to you guys or not, but it may seem like we do a lot of titrations in this class, and we do. But that actually, you know, kind of looking at what we do and as a teacher and everything, I'm not very bothered by that actually. I think it teaches a lot of good lab technique, although you guys are just watching it, so a little bit less because you're just watching it than if you were doing it yourself. But we also do them in a lot of different contexts. Today we're going to talk about an oxidation reduction reaction. It's often you know, an acid-base reaction. So, you know, it may seem like we're doing the same kind of thing over and over and over again, but we put it in a lot of different contexts, and I think having that familiarity of sort of set up an apparatus to introduce a new thing actually kind of helps. So, anyway, that's my thoughts on it. So, like I said, we're going to be looking at the concentration of commercial bleach, and we're going to see you know, check and see what is the concentration. Did I even write in my notes what they listed as? If I didn't, oh, these are the wrong notes. That ain't gonna help. These are the right notes. It's in the worksheet if I didn't write it down. I believe it's 6.0% is what commercial bleach is. Commercial bleach actually, it loses its potency over time, and I should have looked into why that is chemically, like what's happening. But in any case, a bottle of bleach that might have been opened a couple of years ago might not be nearly 6.0%. Now in our lab, these bleach bottles were probably bought fairly recently, so my guess is they're going to be pretty close to whatever it is that the bottle advertises they are. So we're going to figure out, it's 6% by mass. We'll get to that at the end of this, how we're going to figure out the mass percent of these. And so we're going to do this by taking advantage of really sort of bleach's main function in the world, which is as an oxidant, as a mild oxidant. Chemically, bleach is sodium hypochlorite. And it is a mild oxidant. It is a fantastic disinfectant. It can disinfect things at a very astonishingly small dosage. And part of how it does that, I'm going to write it on the board here in a second, but part of how it does that is that it can oxidize, say you have like bacteria. Bacteria has a lot of proteins in it, and the bleach will oxidize the proteins. And once the proteins are oxidized, probably on the nitrogens or sulfurs, once the proteins are oxidized, they make a different shape. Once they make a different shape, then they don't function properly and the bacteria dies. Fungus, it works fantastic on fungus, right? Bathroom or whatever, things like that. So anyway, all right, so what we're doing today is getting a new pen. All right. Okay, so today's goal, we are looking for the concentration of commercial bleach. Okay. Sodium hypochlorite. Okay. Brackets around a chemical mean concentration and usually means molarity, moles per liter. You need to be in the habit of, if you hear the word molarity, you automatically think moles of solute and liters of solution. Okay. That just needs to be absolute second nature. Okay, so chlorite is an oxidant. Okay, we're going to sort of generally abbreviate oxidant or oxidation with OX. Kills bacteria. Oops. By oxidizing its proteins. Okay. And like I said, it's probably the sulfurs. A lot of, not all, but a lot of the different types of sulfurs and nitrogens on amino acids, and it's amino acids that make up proteins. A lot of the different nitrogens and sulfurs can oxidize fairly easily. In the world, in the chemistry world, and looking at different oxidation reagents, hypochlorite isn't a particularly strong oxidizing agent, actually, but it does a pretty good job. Iodine, elemental iodine, I2, not I minus, but I2 is actually a pretty good oxidant as well. Okay. All right, and so, like I had said, how are we going to determine this? The overall plan here is that we're going to take bleach out of the bottle. Okay, bleach out of the bottle is a little bit too concentrated to effectively do a titration of it. Okay, we'd have to use a lot more solutions in order to do that. So if we can do a very careful dilution in the beginning, okay, and then we create a second solution, which is sodium hypochlorite diluted, okay, and we're careful about it. We can figure out the concentration of sodium hypochlorite diluted, and then using our formula for dilutions, we can figure out what the concentration in molarity was for the original solution. Okay, and we're going to put it into a flask. It needs to be an acidic environment in order to promote the oxidation reaction. Okay, and then we are going to add potassium iodide to it. Okay, potassium iodide or iodide is a mild reducing agent, and so it can be reduced or it can be oxidized by the bleach. Okay, so the bleach will react with the iodide and create I3 minus. Okay, now that we could create a very precise concentration of the potassium iodide solution, and if there was a good way to monitor once all the bleach is gone, that would be enough. We could do it. Okay, but for various practical reasons, it doesn't work very well to create a really accurate concentration of the iodide and then somehow follow it. There isn't a good practical way to follow that reaction. Okay. So what we end up doing is just using an excess of potassium iodide, so we know that all the hypochlorite is converted into I3, okay, and the chlorine becomes just Cl minus, all right. And then what we do is we actually take the I3, which is the oxidized version of I minus, and then we're going to reduce it back to I minus, okay? But if we do that carefully, we'll have however much bleach we started with, that's how much I3 we get, okay? It's a one-to-one reaction, as you'll see in just a second, all right? And so if we can figure out how much I3 we have, then we'll know how much bleach we have, right? So we're going to take that I3 minus, I should remind you, and reduce it back to I minus, and that process we can very carefully monitor, okay, and then figure out how much I3 we had originally. However much I3 is how much bleach we had. Okay, that's the general synopsis. Let me put some stuff on the board. Okay, so oxidation reactions. Okay. 2-part process. Okay, so first redox reaction, okay, which is an oxidation reaction. So that's going to be the oxidation of I minus, okay. So we have hypochlorite, aqueous solution, plus 3 I minus, aqueous solution, okay, plus 2 hydronium. This is for the balanced equation, obviously. And that is going to give us 1 I3 minus. That stoichiometry of 1 to 1 there is important. Okay. And then 1 chloride ion plus creates 3 water molecules. Okay. All right. I do want to point out that, or I want to make the point. I already told you, but I want to make the point that that is in excess. Okay. That means we've added, more molecules, more moles of iodide. You need 3 for every one of that. Well, we've added even more than 3, just so that we make sure that this reaction goes to completion. Okay. All right, before we go on, let's confirm for ourselves that an oxidation reduction reaction actually happened here. How do we do that? We do that by checking the oxidation numbers. Okay, so let's box here. So oxidation numbers. Okay. First one is chlorine. So what is chlorine? What's the oxidation number for chlorine here? Okay. Remember, in doing oxidation numbers, a lot of the time you may not be totally sure what all the elements are. Okay, what oxidation number they have, but you may be able to figure out by knowing some of them and knowing the overall charge. So this is polyatomic ion, right? We know that 99% of the time oxygen is a -2. Okay, that's a real easy one we can always, pretty much always count on. So if it's a -2 and the overall charge of the polyatomic ion is a -1, this guy has to be a +1 oxidation state. All right. And then how about the I minus? Well, if it's a monoatomic ion, the oxidation state just equals the charge of the ion. This is a monoatomic, one atom ion. So its oxidation number is the charge of the, actually I should, all right, so in this, in that compound, the oxidation state of iodine is -1, okay? All right, now let's do the same process over here on the product side. Okay, oxidation numbers. Chlorine, we have our iodine. Okay. So we'll do the easy one first. Monoatomic ion, and so its oxidation number is its overall charge, -1. Okay. So the oxidation number of chlorine has become more negative. Okay. And so it was clearly reduced in the process. And then, so I minus, this is a little bit unusual, but we need to adhere to the rule that in a polyatomic ion, the oxidation number of the individual atoms has to add up to the overall charge. The overall charge for triiodide is -1. So the individual oxidation numbers for these guys must be -1/3. Okay? So -1/3. Okay? So that is actually, if it's gone from -1 to -1/3, that has actually become a little bit more positive. Okay? And so it was oxidized. Okay? Iodide was oxidized because its number became more positive. Chlorine was reduced because its number became more negative. Okay, perfect. So I guess I'll make a note here that if we know the moles of I3 minus, it's the same as the moles of hypochlorite. Okay? All right. So as I said, what happens actually is this will turn brown a little bit, but there's no real good way. It just turns brown sort of early on in the reaction, and then it just becomes more and more brown. There's no way to know by monitoring that color or anything like that when you've completely consumed the bleach. Okay? If there was, then this would be enough. We could put the potassium iodide in our burette. Okay? But in fact, experimentally, what's going to happen is we're just going to put this into a Erlenmeyer flask, and then we're going to add the excess potassium iodide. Excuse me. Okay. So, like I said, we're now going to see, well, can we use a titration, okay? Can we use a burette and somehow determine how much triiodide is in there? And you can do that very conveniently by reducing it with a reagent called sodium thiosulfate. Okay. So that reaction, reaction 2, and that is a reduction, capital R for reduction of triiodide. All right. And so that's going to look like, let's see, I'm sorry, I want to make sure I have enough space to do everything I want to do here. Move him up a little bit. Triiodide, aqueous solution, plus sodium thiosulfate. It's actually 2 sodium thiosulfates. That's going to be important. Aqueous, right? And that is going to convert it back into I minus, okay? Just iodide, not triiodide, and then the byproduct of our sodium thiosulfate. Okay, aqueous. Let's check out the oxidation numbers for the second reaction here, okay? So, in the second process, oxidation numbers, look at I, and we'll look at sulfur, okay? Like I said, the oxidation state of oxygen doesn't change very much, and so it's the sulfur whose oxidation state should be changing if this is indeed a reducing agent. So we'll double check that. Okay, so again, we figured that out at the end of this one here. We decided that was -1/3. Okay. Now let's figure out sodium thiosulfate. Well, we know that each oxygen is -2. Okay, and there's 3 of them, so it becomes -6. Okay. We know that the overall of the polyatomic ion is -2, so that means that -4, okay, is being canceled out by the sulfur. Okay, so if -4 is being canceled out by the sulfur, and there's 2 sulfurs, each sulfur must be +2. Okay. All right. So if each of those are +2, that will end up being +4. You add that to the -6, you get your -2. So confirm. Okay. Let's see about on the product side. Okay, we've already done this before for iodide. We know that I-, that's just going to be -1. Okay, so it has become more negative. So triiodide was reduced over this process. Now let's see what happened to sulfur. If that matches, it should be oxidized, right? If this goes as expected. Okay, this is another sort of tricky one. We know that each oxygen is -2, so that's going to be a -12. Okay. The overall charge is still -2, actually, which means that -10 is what is satisfied by the sulfur. Okay. So again, we're going to get sort of a fractional oxidation state, and that may be a little bit awkward to understand. I should have explained that with triiodide. When you draw out the Lewis dot structure of this compound or this compound, you see that there are iodides sort of in different environments and sulfurs in different environments. And so some of the sulfurs have one oxidation number and some of the sulfurs have a different oxidation number, but the sort of the average oxidation number needs to agree with this arithmetic here. Okay, does that sort of make sense? In any case, this needs to account for +10, okay, for this all to work out. So the only way that that can happen is if it is +10/4, okay, or simplified to +5/2, okay? If you have +5/2, you're going to get, this all contributes and creates +10, which added to that number gives you the charge of the overall. Just a little review on how you do oxidation numbers there. Okay, beautiful. Now, as this process happens, it's actually, remember triiodide, that's going to be sort of a brown solution. It will actually become clear, and you could almost perhaps try to do it by just monitoring, okay, when it goes clear, then we know that's the point that this is all gone. Okay, we can do the math and figure out how much we create. It's not what we call a sharp endpoint. Okay, it's a difficult one to call. Yeah, oh, okay, that's the point where it changed. Okay, what you want is a really sharp, where just one drop out of your burette has a dramatic, or maybe 2 drops out of your burette has a very recognizable change. Okay, does that make sense? We don't want that to happen over many drops. All right. So it turns out what we can do is we can add starch to this, and starch actually makes a complex with triiodide that is a very deep blue color. Okay, it does not do that with iodide. All right, so if you add in starch, you get a dark blue color. Okay, starch indicator. Okay, and this into the reaction, and this is a nice sharp endpoint. It's colorless. Okay. All right. Yeah, it's going to be. Well, before I tell you what it's going to be, remember that if you have 2 simple processes, okay, and simple reactions, and some of the products created in the first one are the same as reagents in the next one, you can actually cancel those out and you can get what is the overall chemical change here, okay? Because we know that ultimately iodide is not changing, okay? All right, so let's do that and see what the overall reaction is. Okay. Overall reaction. Okay. So, and it's important that they have the same coefficients, so one triiodide, one triiodide. Okay, so they have the same coefficients, otherwise you wouldn't be able to cancel out all of them, just some of them. Okay, so that cancels, okay? And then you have just regular iodide on the product side of your second process, which is on the reagent side of your initial process, okay? And so that's basically it. You can cancel those out. So the iodine actually, because it's unchanged, isn't part of the overall reaction. Okay, let's write the overall reaction. Sodium hypochlorite. Okay. Plus sodium thiosulfate. Turns into 3 iodides. Whoop! Sorry, I was looking at the wrong thing. And I forgot my acid. Plus 2 hydroniums. Okay. Turns into chloride ion. That's 406. And 3 water molecules. When you go to do my worksheet for this, you'll see that it sort of don't have you just pay attention to this reaction, actually force, sort of walk you through both processes, because I want you to be appreciating both, that both are happening and sort of appreciating the stoichiometry. And so I want to remind you, watch stoichiometry. Okay, of equations. Remember, stoichiometry is how much you need for each, right? For each chloride ion, you need 3 iodide ion, or I'm sorry, for each hypochlorite ion, you need 3 iodide ions, so forth and so on. This is how much you need of each. Okay. Yeah, and then also you want to pay close attention to how many molecules of sodium thiosulfate you need for each molecule of triiodide. Okay, a few more details that, that's about it. It's fairly straightforward actually, but there are a few more details that I want to help you appreciate. Okay, so some extra details. The first thing I want to remind you that I mentioned earlier, that we are going to dilute the bleach out of the bottle. So by doing the titration and everything, what we're figuring out is actually the concentration of sodium hypochlorite diluted, okay? And if we do that carefully, then we can use our formula for dilutions to figure out what was the concentration of bleach concentrated, or out of the bottle. Okay? All right, so extra details. bleach out of the bottle, diluted. Okay. For added to reaction. Okay. Specifically, it is 10.0 mLs of concentrated, okay, diluted. Okay, it's put into a 100 ml volumetric flask and diluted to 100 mils. Okay. All right. So, once we determine concentration of hypochlorite diluted, okay, we can calculate the concentration of hypochlorite out of the bottle. Okay, how do we do that? Do that using, sometimes some teachers use V1, M1, I use VD, MD. So VD, MD equals VC, MC. Okay, so this is the volume of the diluted solution. This is the molarity of the diluted solution. This is the volume of the concentrated solution. This is the molarity of the concentrated solution. Okay. As always, I strongly suggest that you rearrange before you plug things in. Yeah. And so what we're going to be looking for in the end, we'll have figured out this through our titration process. And then what we're going to want to do is we want to find out the molarity of the concentrated. Okay, so you can rearrange put the C on the denominator, or the VC on the denominator over there, and plug in your values, your 10 and your 100, and then the concentration, the molarity of the diluted stuff that you figure out from the titration process. Okay, what I'm going to mention right here. All right, so 2. Initially, want the molarity, that's sort of our initial goal before we do all this stuff, of hypochlorite diluted. Okay. Molarity, moles of solute, moles of hypochlorite, liters of solution. Okay. I'm really spelling things out here, I hope not too much, but don't have much left here, so video's over short. Okay, so moles of diluted, which we need, right? That's our numerator. That comes from the titration. Okay, and then liters of solution of our diluted stuff. Okay. Yeah, I didn't write that down. Shoot. Okay. Well, it's in the procedure. Yeah, and it'll be included in the data too, just as a reminder. I think it's 25 mils, but I can't guarantee it. Okay, so the liters of solution is what you first put into the some sort of volume of your diluted solution that you created up here. Put in to a 250 ml pearl flask or beaker. Okay. All right, one thing I want to point out here is a pitfall that some students can sometimes fall into. You're going to put a certain amount, and it's important how much you put because you need to calculate the concentration at the end. Like I said, I think it's 25 milliliters, but I can't guarantee it. Sorry. But you're gonna put some specific volume into your flask, okay? And then you are actually going to add some other solutions. You're going to add acid. You're going to add potassium iodide, okay? That volume of potassium iodide and that volume of acid, do we need to account for those when we're figuring out our molarity? Okay? We don't actually have to, all right? Because that would be, yes, technically, we've just done another dilution. We've added some acid. We've added some potassium iodide, and that's diluted what's in there, okay? But we're not trying to find out the concentration of that solution in the beaker, okay? We're trying to find out the concentration of the stuff that we originally poured into the beaker before we started diluting it and stuff, okay? So that won't change the number of, when we add the other solutions, that's not going to change how many moles we put in there of hypochlorite in the beginning, nor will it change what volume of the hypochlorite solution we put in there. Okay? Put that note down there. Note. Add other solutions. Lost my place. To beaker. Okay. Does it matter to your molarity of hypochlorite diluted? No. Okay? Because doesn't change, these extra solutions you're adding doesn't change A or B, A and B. Okay. I'm going to put in the video in text on top of the video what this actual concentration, what the volume is that you put in there. Okay, so you don't have to worry about where you're going to find that and stuff. I will put it in the video right there. Okay, see how that works. Enjoying video editing, but I should probably keep my data out. All right. We get bored this. Last thing I want to talk about is so you'll figure out the concentration of the diluted. Okay. The process is going to tell you the moles of hypochlorite in the diluted solution. The thing that's going to be right there is going to tell you the liters of it. Okay, and then we will use the dilution formula to figure out the molarity of the bleach right out of the bottle. Okay, but when we have the bleach right out of the bottle, we want to be able to convert that into mass percent, right? The value that we have for regular commercial bleach isn't in molarity. Okay, it's in mass percent, so we want to be able to make that conversion. A nice way to do that type of thing where we don't have a specific amount that we're trying to convert into, we're just trying to convert a ratio, okay? Molarity is a type of ratio into another ratio, is pick a volume, okay? Or pick a specific amount, I should say, in this case volume. All right, so what I recommend if you're trying to go from molarity to mass percent, just pick 1 liter, okay? You figure out, okay, well we know we have whatever molarity we end up having, okay? So, well what if we had 1 liter? Then we can easily take 1 liter and the molarity and figure out how many moles we have, okay? And then if we have the moles of hypochlorite, okay, we can figure out the mass of hypochlorite that we have, okay, by using the molecular weight of sodium hypochlorite, all right? We need to remember about the sodium here because that does contribute to the mass percent, okay? When you're talking about molarity, you don't have to worry so much about the sodium because the molarity of sodium hypochlorite is exactly the same as the molarity of sodium hypochlorite because there's one sodium for every one of those, so it doesn't change. But in the when you're figuring out the mass percent, you do need to include the sodium. So if you know the number of moles of sodium hypochlorite, you can convert that into mass of sodium hypochlorite using the molecular weight of sodium hypochlorite, okay? You can calculate that out by hand, or you can get it from the internet, I don't care. And then, so that will be the that's our numerator, okay? Then we need to think about what is the mass of our solution, okay? Well, we can use the density, the known density, that's in the worksheet, by the way, the known density of bleach out of a bottle. Okay, that has a very specific mass per liter or per milliliter, it's probably expressed as. It has a very specific density, and that'll give us the mass of the solution. Once we have the mass of the solute, okay, that's our numerator. The mass of the solution is our denominator times 100, and you have mass percent. Okay, all right, so let me put that on the board real quick. You're all done. All right. Okay. Converting molarity to mass percent. Okay. So reminder, mass percent equals the mass of the solute, okay, over the mass of the solution times 100. Okay. And when you're figuring out the mass of the solution, you don't need to do something wacky like add the mass of the solute to that. That's already incorporated in the density. If you have the density of bleach, it's not the density of water, it's the density of bleach. So that's already factored in using the density of bleach. Okay, so process that I just said to you. There's other ways to do this, but I think this is kind of the most straightforward. That you have exactly 1 liter. By the way, if you're going to be doing math with this now, this doesn't limit your significant figures. It's a hypothetical thing, so hypothetically you have that as accurate as you possibly could have that. Okay, so the only thing that you're limited by is the molarity that you use, and that's determined by you know, the concentrations and the volumes that you use out of your blah 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 blah. So in any case, this is don't the fact that I wrote 1 there, don't trim off significant figures. Okay, so if you pretend you have 1 liter, then you can get the moles of sodium hypochlorite from capital M, always means molarity of sodium hypochlorite, which is what we just figured out, right, above. Okay, and so we'll have the moles of sodium hypochlorite. Then we can get the mass of sodium hypochlorite. Okay. From the molecular weight, sodium hypochlorite. By the way, I don't really like using that phrase, molecular weight. What you're really using is molar mass. Molecular weight is the mass of one molecule. Okay, so it's kind of imprecise. Start throwing around molecular weight. It should say molar mass. The problem is the whole world is sloppy about that. So the whole world throws in the word molecular or the words molecular weight when they mean molar mass. Because we want to know what is, don't forget it's the same digit, or it's the same digits, just different units. Okay, the mass of one molecule is the same digit-wise, or the same number as the mass of one mole of it. Okay, it's just here it's in when you're talking about it's in AMUs or it's in grams per mole. Okay. All right. So since the whole world commonly makes that mistake, I want you guys to not be thrown by that. We're out in the world and people are being imprecise about their language. All right. Then you can get the mass of solution, okay, from your 1 liter that you just out of the BLEACH. If you want to choose 1.5, then you can, or some other value, but 1 makes it pretty simple. Okay, and the density of the solution. Again, that's in the workbook or in the worksheet. Okay. All right, beautiful. There are a number of different trials. You're going to have to calculate an average. You're going to have to create a standard deviation for your average, and you all know how to calculate a standard deviation. If you don't, that's an easy look up. And then you're going to have to calculate a relative standard deviation. Okay. The worksheet walks you through how to do a relative standard deviation. Okay. It's basically the standard deviation over the average. Right? That's it, guys. Yeah, have fun. See you next time.